All right, hello everybody. There will be some difficulties today, or at least on my side. I was sick, and I'm still not maybe not very coherent. And if I start coughing, maybe I will wear this. It's like from the COVID times. Now, the other difficulty is that somewhere this summer my old laptop has went under the rain, and some of the lectures in the keynote form they got wet, and then so I have only the PDFs for some lectures, and I am gonna remake them, but for this one I was not able to. So it's still called lecture 3, and I know there are a few errors in that, but otherwise it should be fine. All right, and so okay, so the idea for today is that we discuss what is backpropagation from the point of view how we like, if we like to do something analytically with that, what it means, and how it works from the mathematical side, and also like from the practical side, what it means for if you want to use differentiable optimization for big models such as neural networks, how we implement such automatic differentiation procedures efficiently, how the library is doing that, and what we can customize if we need, what the library can do for us. Yeah, okay, and so from these two sides. And then also in the end we can speak beyond this standard backpropagation procedure. For example, we will consider, well, actually, we will consider implicit differentiation. So that means you don't have like the feed-forward function defined to differentiate, but you have maybe some optimization problem or some equation whose solution is supposed to be used downstreams in some processing. So we can talk about that as well. At least an overview of how it works in such cases. All right. So we start from kind of recalling these basic concepts, and in particular the concept of derivative. It's kind of sophisticated in different cases and in different situations, and like one-dimensional functions, multivariate functions, some functional spaces or whatnot. So to kind of gather for the purpose of our needs the correct definition of the things. So for us, like intuitively, I want you to view the derivative as a linear approximation to the function, well, up to the sort of shift in the vertical axis. So, but the purpose is that, okay, so we're gonna just take our function, however complex it was, and at around the current point approximate it with a linear function. That's, in this case, it's a hyperplane. And then the slope of this linear function is our derivative. So we can write it in this form, so that around the current point, so if you displace from some current point by delta x, then we want this to be approximated by the value of the function at that point, plus this kind of linear part, which is linear operator acting on the vector of displacements, and plus something which is small enough with respect to this the distance from this point at which we are approximating. So that's the area. So that kind of this linear approximation should be close enough to the true function, and if that's the case, that's called so this linear part is called this j, this linear operator is called the derivative. And yeah, once it exists, it's unique. And once we express it in coordinates, then it's called in that context a Jacobian matrix. So to clarify this a little bit, so this is kind of this formalism is designed specifically for the function which acts from m-dimensional space to n-dimensional space. So the input is a vector and the output is a vector. And then when expressing this linear operator, the derivative for this kind of functions and coordinates, we obtain such a matrix. So this Jacobian matrix is matrix of these partial derivatives. Now, if you recall, like the matrix vector product, you are getting that increment along axis x1 is multiplied with the partial derivative of each coordinate of f with respect to the x1, right? So then you have like the total increment of the first coordinate of the function is given by this like sum of the kind of steepness of the function with respect to that variable multiplied by the offset in that direction. So I am like visualizing this to show that it is this matrix and not the transpose of this matrix, so that how the columns and rows are organized here. And they are organized in a way that, like, look, if you had a function f of x ax, then we want that its linear approximation would be, obviously, we would like to have f of x plus, okay, x0 plus delta x. Let's do it formally from this definition. So you will have f of x0 plus what do I want to say? So plus j delta x. So that's on one hand, this is what we want as an approximation. And on the other hand, we know this is a x plus delta x. And okay, automatically from the linearity of this, so something cancel. So this is ax0, right? So this cancels with this. And we have that from this we conclude that j must equal to a, right? And then that's our best linear approximation is a delta x. Yes, what would you expect, right? So if it was a linear function, then the derivative is the linear part, the linear operator, and the linear approximation is the original function itself. But because of this reason, because the linear functions are written like that, or because of the convention that we start from the mapping from the row vectors, m-dimensional to n-dimensional row vectors, then it implies that this Jacobian matrix must be of this shape, and the partial derivatives must be laid out in this order. Let me comment also on the but maybe I didn't get this. On this little O notation, is everybody comfortable with that? So it depends on the context, right? So if you do analysis of algorithms, typically you consider the infinity limit, and then O notation, this little O notation is that the function is asymptotically at infinity below some other function. But here we are considering the limit delta x goes to 0. And in this case, this little o notation means, like if you say f of x is little o of g of x. Okay, let me be specific maybe. And right here, this okay, yeah. So I say like f of delta x is of delta x if the limit if this limit is 0. So that means kind of, so this is delta x. Then the function approaches 0 faster than the linear function asymptotically when delta x goes to 0. So that's what it says. And it says that, okay, our derivative must be accurate. So sort of our linear approximation must be accurate in that sense. That there is a linear part and then some reminder that that approaches to 0 faster than any linear function. Maybe also would be useful to link this definition maybe to the common definition that you know. For if you have a function of one variable, right? So if you have a function like real to real, and then what's the derivative? That's the limit, right? So it's some limit epsilon going to 0, f of x plus epsilon. Okay, I could write delta x for epsilon to make it consistent, right? So we are considering derivative at x0. It is this limit, right? So increment of the function to the increment of the argument. And let us do maybe reinterpretation of this equation. So I write here like minus f prime of x0 and here 0. And I can put this part to the numerator. So what should I do? To multiply it with delta x, right? So then I will write here minus f prime x0 delta x. And now you see that it's equivalent. So here, this was our original function at the argument x0 plus delta x. This is our linear approximation, f of x0 plus derivative times delta x. And the limit says it must be 0, so that's exactly what we wrote. You said, okay, so this is this little o of delta x. And we were kind of just equivalently rewriting this definition for function of one variable, but now this can be adopted to the function of multiple variables by saying that, okay, so this is some norm of delta x. Yeah, what else to say about this? So what we're gonna do with these linear approximations is that if we have a complex function which is composed of multiple functions, we're gonna linear approximate every function in that composition and then compose these linear approximations. This is going to be linear. And if we have like a big loss function, which is sum of all of the training data of different losses, then also we're going to approximate every term in this sum linearly, and then sum of these approximations is again a linear function. So this is kind of closed in approximation infrastructure. So we're going to approximate everything linearly, and then we could work with any model and with any big training data. Okay, so like except of the derivative, so we talked about derivative Jacobian. Let's also link it to, so we discussed the definition for derivative of function of single variable. Now this is exactly this definition for the partial derivative, right? So this Jacobian matrix is a matrix of these partial derivatives. And it's natural that this limit we can approximate by a finite difference, right? So suppose we have some function which is given by a black box, and we want to somehow approximate its derivative, then we could straight away use this definition with some small but non-zero epsilon and approximate this numerically by just incrementing the argument in a particular along a particular axis. This is denoted as this axis I here, and then like taking this finite difference and dividing by the step length. Now about this finite difference approximation, there is a so we have a function of multiple variables, right? And we are talking about its partial derivatives with respect to x. So this let's say coordinates, the input coordinates, and then like what we're gonna do is to step along of each of these coordinate axes by an epsilon. So this I denoted like a basis vector. So this would be E1. This is E2. And the trick about these finite differences is that if the function is smooth enough, so that's twice continuously differentiable, it turns out that this one-sided incrementation, so that so you take what's that, x and x plus epsilon points, and sort of put a line through these 2 points. That's our linear approximation. That's from the finite difference. Well, it turns out that if you do instead this, so if you instead consider the point x minus epsilon and the point x plus epsilon, and put the lines through these 2 points, this is going to be like more accurate numerically. So with the same size of epsilon, you are getting the accuracy, which is one order better accuracy from this numerical approximation. And this is then also like if you really have a function given by the black box, but we assume that it is smooth enough, then using this numerical scheme would give us in practice, if we so in practice we have finite precision arithmetics to evaluate this function and to calculate this division, right? So if we really take very small epsilon, this is going to be numerically, the numerical errors will destroy our estimation. So in practice, we have to kind of trade off to keep this ratio still numerically precise enough and to keep the epsilon small enough such that this finite difference is a good approximation of derivative. And what this tells us that with this symmetric difference, we're gonna be more accurate with the same size of epsilon, which is like far enough away from 0 for the numerical precision to work. how this can be useful, it's, yeah, okay. One thing is that you have maybe some sophisticated function for which you have implemented analytic solution, but you want to check it. And then this is like a straightforward way to check that your derivative computation was correct. The other application could be if you have something which is not obvious how to differentiate. For example, you have some numerical solver that solves some system of polynomial equations, and it is maybe depends on only few inputs, and in this case it is just cheaper to compute these finite differences with respect to each of the inputs. Like, okay, so that means we will need to compute this evaluate the forward of this function in the as many times as there are coordinates, as many times as there are inputs. But maybe that's cheap for some small problems. But in the end, we will consider also this implicit differentiation. So we should be able to do this for a solver also efficiently in the other way. Yep. Oh. Yeah, it is the epsilon. This is what I was trying to explain, but it is we need to, so epsilon is scalar, right? But we are talking about partial derivatives. So the function which is in two coordinates, to calculate a partial derivative with respect to x1, we need to offset our current point in the direction of the first axis. So e1 is not e to the power 1, but it is the basis vector which has the coordinates 1, 0, right? And that one has the coordinates 0, 1. It is up to one's convention and notation. Sometimes we need to work with some vectors, right? And then it's usually xi. And let's say if it is a vector of inputs to some neural network, I would denote it as xi. A particular coordinate of that vector is xi. But then if there are maybe several layers, I need one more index. So I would usually, for the layers, I would use the upper index. So this would be xi0, and then some processing, and then this creates x2 and so on. Just, yeah, so here it's E1 is a vector itself. If we needed to index its coordinates, that would be the lower index. But it is, of course, arbitrary, right, where you put it. If you had some tensor analysis books, they had many indexes everywhere, like here, 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 also. But please do talk about such things, because if notation is confusing or something is not clear, we need to clarify this. Okay, so we discussed derivative, Jacobian. We discussed partial derivatives and these finite differences. Then, like, let's also get it clear what's the difference between derivative and gradient. Kind of for a function of one variable, there is no difference, right? So we could call this slope k a derivative, or we can call it a gradient. For function of multiple variables, there is this kind of technical nominal difference, if you like. By that definition of the derivative and Jacobian, it turns out that if we consider a scalar valued function, then its derivative is a row vector. So it needs to multiply the column vector of increments, so it gotta be a row vector. And gradient is defined to be a column vector of the partial derivatives. For reasons that suppose you want to do gradient descent, then from the column vector of your current point, you want to subtract a column, some other column vector, and that column vector is then taken to be proportional to the gradient. Why we would do that? This is also linked to the the following question: what is the step in this space of the arguments which ensures the steepest increase of our linear approximation if we bound this length of the step by some value? You can write it as a small optimization problem. So this is our linear approximation to the function given by this derivative times the increment plus this constant offset. And you want to maximize the value of this linear approximation subject to that the argument stays in this ball. And the solution of that, you find out that it is by kind of formally solving this, you find out that the solution is that this transposed Jacobian, which becomes a column vector and normalized, right? And then this is consistent with the notion of steepest descent if you are maximizing, or the steepest steepest ascent if you are maximizing, or steepest descent if you are minimizing. So if we start with this formalism, then we're gonna be working with derivatives as row vectors, and we will do this for some times. But then if we kind of at the point when we switch to the optimization to the gradient descent algorithms, we're gonna reshape them into the column vectors, so rather as this gradients. And of course, this formalism has limitations, right? So it's if a function takes an argument, a matrix, and we want to find linear approximation with respect to this matrix, right? Not just a vector, but a matrix. Then this breaks down because you cannot form then any more such a nice Jacobian matrix. There is still a derivative, but you gotta write everything in coordinates. Like if you have some function of matrix W, right? So we will need to write df I d w j k, and this has 3 indices. You could name it somehow, but it's not going to be like multiplying matrices in the linear expressions. So what I was saying, yeah. So that kind of this is a nice formalism that allows us to write things with matrices and vectors in some simple cases. But in more difficult cases, you kind of out of this formalism, and it could be a little bit awkward. So let's say if f of x was ax, we discussed, right? So the derivative is also often denoted as this. So the derivative is a, right? But what if I tell you that f of x is the x transposed a? Then it's a bit confusing now what you formally have to do, because now the result is the row vector. So it's not fitting exactly to this formalism. So the result of is the row vector, and then what should be the proper shape of this matrix for the derivative is not clear. We can reinterpret this function as a column vector, but then for that reason I would have to transpose both sides, right? So I have to write something like this, and then the derivative would be a transposed, right? Obviously, but if you want really this function to be a row vector and ask for derivative of that, then we are kind of out of, so this formalism cannot like really precisely handle this case. Then we can work with coordinate notations. I feel like I'm already reiterating on this topic too much for the derivatives. So let's move on. Now, what will be important for us is composition. So because neural networks is kind of, you do many operations and then you apply, so you process by steps. So you take some inputs and then you do one kind of processing, then some other kind of processing, some third kind of processing. So this is all like composing the processing steps. So mathematically, it's like a composition of different functions. And let's do an example for, again, for one-dimensional function, as simple as this. So I take some function, which is the square root logarithm x squared. All of you already know how to compute derivatives. You would say immediately, okay, f prime of x. You start doing it analytically, right? So you know the chain rule. So you do 2 square root log x squared, and then you differentiate what is in here, again analytically, so it's 1 over x squared, and then you differentiate that, and this is 2x to x, and you maybe cancel something here. So and you say, okay, my derivative at any point x is this. But what we're gonna do now in this slide is to do it kind of algorithmically, not analytically, but algorithmically, and for the purpose of evaluating the derivative at the current point only, right? So this is a function, this is a derivative as a function, but what we need really for the optimization is just the value of this function at a particular point. So, and kind of to represent this algorithmically. So how are we gonna do this? So we do, first we compute the value of the function itself. So we take some argument and evaluate, like, okay, this composite expression we evaluate inside out. So we compute x squared, then we compute logarithm of that, and then the square root of that. And now we view it as a composition of these three functions, and each of these functions we approximate linearly at the current point. And then the derivative is a product of the slopes. So this is basically our algorithm. What it has to do is to, on the forward pass, it has to evaluate these functions and maybe remember the point at which the function was evaluated. And then to compute the derivative, we need to compute these slopes at these remembered points and just multiply out these slopes. So this multiplication of these slopes can be done kind of in any order for this composition in one-dimensional case. But let's just consider now a general case. So if we have a composition of multivariate functions like this, then what we are multiplying is kind of their linear, so a linear approximation to each of these functions. And okay, so maybe basic case is that if our function was just composition of linear functions from the very beginning, then obviously its derivative is this product of these matrices AB, right? And then if it was not a composition of linear operators, but it was some nonlinear functions, then each of these functions we kind of approximate linearly. And these approximations are given by these derivatives. Yeah. One, I forgot to tell you about this notation stuff. So usually Jacobian, the usual notation for this Jacobian is that to say g sub x, it means derivative at a point x. That's like a common notation. But here, the point at which we are calculating the derivative is fixed by the context. And instead, we need derivatives with respect to different parameters or with respect to different intermediate variables in our computation. So we're going to be using the notation that there is saying, okay, so it is the derivative of function f in variable x. You see, so this is j f derivative with respect to x. And now it should make sense, this formula. So this says the composition. So we take, so this is derivative of f in g times the derivative of g in x. And this is our chain rule, right? So if you expand this in coordinates, it looks something like this. So we sum up over all of the possible coordinates of g. And then, okay, how fast f changes with case coordinates of g times how fast that coordinate of g changes with the j's coordinate of the input. And so we sum up all of this all these effects. Am I still understandable? Okay, thanks. So now let's see what happens if we apply it to sort of neural network, some feed-forward neural network, which is the composition of, let's say, these three functions. So we have we have loss function, and then f of g of h of x. There is one more shorthand notation that says, okay, so often we are interested in the derivative of the loss function with respect to particular inputs. And so I will abbreviate this as just j sub x. So this will be derivative of the loss function with respect to the particular intermediate or input variable x. And now what do we do? What do we need to do to compute the derivative of the loss with respect to let's say, to the input x? As we said, so this is the composition defined in the function, and the derivative is composition of this linear approximation. So it's just the product of all these Jacobians so a Jacobian for each of these functions. So we just take matrix product of these Jacobians in the same order, exactly the same order as this composition was written out. Now it's the time to discuss where is the backpropagation and with respect to what it is going backwards. Because in this, for example, in this representation everything is in the same order. So this is composition of functions. So this is composition of linear approximations of these functions. So what exactly we are doing backwards? The trick is about that. Okay, so our loss function is a scalar value. It's not a vector function anymore. Our loss function is some number that we're gonna optimize, and its derivative is a raw vector like this. But the derivatives of these intermediate layers, which are typically like, okay, you take a vector input, you produce a vector output, like multiple input neurons, multiple output neurons. So their derivative are going to be some matrices, not necessarily square if this number of neurons is changing, but I assume for simplicity that they are square. And now, okay, so product of these Jacobians, we could like visualize as product of this row vector with some matrices. Now, the question to the audience. So what is the time complexity to multiply two matrices of size n times n and n times n. N cube, yes. This is n cube. And the time complexity to multiply one vector with a matrix. Okay, yes, so that's n squared. Good. Now, what is our goal? Our goal is to compute this product. And this product is associative. What it means that you could compute it sort of where did I put the color chalk? Okay. Associative means you could maybe first compute the product of these two matrices and then multiply with that matrix. Or if there are more of them, you could do like this, right? So compute product of these two in parallel, maybe compute the product of these two, and then product of these two, and then you multiply something else. So it does not matter where you put brackets, so that's associativity. But assume that there is already enough parallelism in okay, so forget about this computing this and this in parallel. So suppose we have to do it sequentially, then what would be more efficient, right? Which order would be more efficient to compute the result of this multiplication? Yeah, yes. So that's the point. So if you have this row vector, multiplying it with the matrix is unsquared complexity, and then the result is a row vector again, and then we could like keep reducing this, and this will give us the total complexity kind of n squared times the number of these layers. Versus if we start multiplying these matrices, we're gonna get n cube somewhere, and so that's not as efficient. And only for that reason we are doing it like this. So this is done in this specific order. So it is why it works, because we have a scalar valued function, right, of which we want to calculate the derivative. And then it's convenient to compute it in this way, or cheaper to compute it in this way. And now we have like a forward computation which evaluates this composition inside out, that we say, okay, take the input, compute H, compute G, compute F, compute the loss. And then we have this backward computation that says, take derivative of the loss, multiply it with Jacobian of F, multiply it with Jacobian of G, multiply it with Jacobian of H. So kind of in the backward direction. Yeah, okay, I have a slide for that, but I already explained with hands. So this is, let's say this is our network, maybe we also with some input and with some weights. Now to compute the derivative with respect to the input x, we discussed, right? So we need to take the gradient of the loss, derivative of the loss, then multiply it with Jacobian of f, and then do it along these red arrows, and in each red arrow we like have the current row vector, so that's the derivative of the loss with respect to the output of this layer, and multiply it with the Jacobian of that layer, and that gives us the derivative with respect to the input. If there are some more inputs, so this okay, so there is a similar chain with respect to the other inputs, and this part is shared, right? So if suppose that this x is fixed and we are now kind of just varying the w and want the derivative with respect to w, then if we repeat all the derivation and calculation, we find out that it's going to be composed of the same sort of part of the chain rule for this f and the loss, and the only difference is then this, so this Jacobian of the function j with respect to the weights w. So we like just in this final step we need to multiply in the currently reduced row vector or this um, with the Jacobian of with respect to the weights. Yeah. I see people nodding. I guess we understand that there are input images and there are parameters of the network that we want to learn, and here the weight is the parameters. Why we would want the gradient with respect to the input? For the reason of generality, and so assume that there are more processing blocks which produce this input, and we eventually want also to find gradients with respect to parameters of that blocks. So we, to start with, we need also the gradient with respect to this input. Okay, I think it is more clear now from what we have discussed so far is that basically all this procedure is modular, right? So we can compose the neural network out of different functions, and for each function we need these two things. So okay, to be able to compute this function forward, given the input and parameters of the function, and to be able to, if you have the derivative of the loss with respect to output of this function, then we need to compute what is needed on this backward computation is to multiply this derivative with the Jacobians of this function with respect to the all its formal inputs, right? So the weights and the in kind of the whatever the neuron activations. Okay, so and this also gives us the way how to implement things and do everything in automated way. So basically then we need for each function that we are going to compute, supply also this type of procedure, and then we can compose kind of any network out of that and more or less automatically be able to compute all the gradients. Yeah, there are many reasons to compute derivative with respect also to the image. If maybe you want to see what pieces of image influence our loss the most, or maybe you want to make an adversarial attack to confuse the network. We will talk about this in few lectures. Yeah, so this is like now just a note. So if you want to express gradients, so the thing that we're gonna use in the gradient descent, then this rules gets transposed, right? So you recall that the derivative, so gradient of scalar valued loss is the transpose of the derivative, and for that reason, the kind of backpropagation rule for the gradients looks like this. So it's the transpose Jacobian multiplied with the gradient now on being on the right. Anyway, so yeah.
Just a very quick question: how much points would one potentially lose at an exam if you were not to remember like which one of is the row vector, which one is the column, and just like get the general idea right?
So at the exam, you will have problems to solve, and we will try to make them as unambiguous as possible, and also maybe self-contained in the sense that you will not need to remember what is some complex kind of functions or the complex notation that we used throughout the course. But having the idea may not suffice. You need to then solve it correctly, right? If you do it in your notation or in our notation, it does not matter. So if you're able to solve it, yeah, fine. If you know the chain rule, you are fine with that. Uh, so maybe then this whole thing about backpropagation is, you know, in neural science it was proposed or presented in some cases as a know-how, as a separate algorithm for training neural networks, right? Some error backpropagation with the 4 rules how these errors should be backpropagated. But if you know the chain rule, it is the chain rules. So then why don't you need the rules of backpropagation? Now we discussed what we've done so far. So we discussed, okay, so what is the derivative? What is the how the chain rule occurs thanks to the product of these Jacobians, if you approximate every of the function in the composition. And then like, okay, now this notation looks a little bit complex, but so you just comment on this caveat that the derivative in the gradient and formally not exactly the same. Okay, now example, and example is, yes, out of this formalism already. So what we took in this example is correlation layer. So we have some input X, and then we want to have like a sliding window with weights, and at the output location J, we want to sort of look at the neighboring locations in the input and multiply it with these corresponding weights and sum up. So this is this like little one-dimensional correlation layer. And we already would have maybe, it's possible to represent it as a, in this formalism as the matrix vector product. But we don't have to do this. So it's easy actually to do it in coordinates. So how we do it in the coordinates? So you know the total derivative and the chain rule. So we need to calculate derivative of the loss with respect to the coordinate xi. We need to sum through all possible coordinates of y and to have this chain rule. And how it works then, so okay, so we substitute here derivative of the loss with respect to the one coordinate of the output. That's going to be this what we have, what our backward function receives on the input. So this is gi, and then the every output with respect to every input. So the output is we substitute. So this is the sum. So the derivative can be put. It's linear, so it commutes with the sum. So we could put it through the sum. We could differentiate this xj x sub j plus k with respect to the coordinate xi. And now we can, like in these coordinates, what we formally do is that, okay, so this is going to be 1 if the index j plus k equals to the index I. So otherwise, we are differentiating with respect to some other coordinate, and that's 0. And so this is what is written here. This is the Iverson bracket notation that says, okay, this is 1 when this equality holds, and 0 otherwise. And once we have this Iverson bracket, then one of these sums can go away. For example, we could say that, okay, so we just substitute for k, we substitute from this equality that k equals to I minus j, right? And then we have this. Or we could rewrite it also in the other form by saying that, okay, j must be equal to the I minus k. So let me write it down. So we could say it equivalently also as the sum over k, wk, and then x. What did I say? The no, not the x, but j g with index I minus k. Thank you. And you recognize maybe that this is a convolution. So we started from some correlation with the plus here, and here we found that the derivative, the backpropagation computation, should compute something like a convolution of the incoming gradient of the loss function with our weight kernel. But maybe interesting exercise, right? To observe. Okay, and also like one more takeaway from this is that both this forward pass, this convolution, so if this weight kernel is of some small width, so this filter is of small width, then this convolution can be computed in linear time in the length of the input, and also the backpropagation can be computed in the linear time in the in these dimensions. So in fact, like for this simple correlation or convolution, we could do both forward and the backward in the linear time in the size of the input. So that's we were talking about multiplying this row vector by the matrix that was n squared. But in for many operations, and this is by design, right? Because we like to have cheaper constructive elements in our neural networks. So if you use convolutions, then it's linear time, both ways. Okay, now we go like a little bit towards the practical side of this. Now, how this is gonna work? So we discussed that things are modular, and we need for each layer we need a forward and a backward, and then we can compose any neural network. So how is it can be implemented and sort of conveniently done by the library for us? So how it works with the help of PyTorch. So maybe the currently most convenient way how to define this neural network and define which blocks we compose in which form is just by computing things. So this is an example. Suppose we want to construct such a neural network that has a linear layer softmax and some loss function. There is a level of abstraction that says, okay, we have some model which implements a linear layer and it has some parameters, and the model that implements softmax and the model that implements cross entropy loss. But this is kind of just convenience, higher level abstractions. If you want to customize things, you might want to do this on a more basic level of abstraction. And on that level, it works as follows. So you just compute what you need. So how we can do this? So we say, okay, then we declare some parameters. So there's going to be some tensors of some shapes. And then we assume we have some input, for example, some random input of some shape. And then what we do, we just compute what we need. So we just take our input, multiply, do this matrix vector product, add the bias, then run some function on the result, and then compute the loss as some, okay, also what we discussed. So this is the cross entropy loss. So this maybe one hot tensor representing the class. So we are doing maybe classification example in this case with the logarithm of these predictive probabilities, and then sum up all these negative log likelihoods, and this is our loss. The point is that while when we create the parameters and we create the inputs, they are all of special tensor class. And whenever you do some operation on these tensors, the library tracks which operation you were executing. And at the end of this computation, so when you have computed the loss, so it has an implicit representation of how it was computed. So it has the computational graph. It remembers in some form this computational graph. So how from your inputs, using which operations, elementary operations on tensors, and which inputs were connected where. So it creates such a graph. So basically every operation remembers what were the inputs to it, and it remembers the type of the operation. And then once this graph is somewhere internally represented in PyTorch, it can easily do the backward for us, because it would just go backwards in this graph, and then it knows the operation, it knows from which input it was computed, so it means that it could do this, compute the corresponding backward operation needed for that block, and sort of backpropagate it through that graph. Now, yeah, at some point, I don't know, depending on how much you know about the current state of the art. So we started from, like this multi-layer perceptron architecture, and now I'm telling to you, okay, you do whatever computations with tensors, and we can backpropagate that, and we can train that, and this is going to be our neural network. So it's not necessarily any kind of neurons or any kind of MLP. It can be pretty much anything. In this case, what you can compute in the what you can compute sequentially in the feed-forward manner, right? So here there are still no loops or equations involved. So it is, if you are able to compute something in a feed-forward manner by some sequential algorithm, then you can also train that, and this automatically, right? I mean, backpropagate it automatically, get the gradient, and then we can train that. To detail this example, so suppose this is our computation graph. Then from the practical side, there is also the question of efficiency. So if we backpropagate each of these operations individually, we need to remember something for each operation. We need to save at which point this operation was executed for computing this linear approximation, for taking the slope or the derivative at the correct point, right? So every operation, it would need to remember something to compute the correct Jacobian or the product with the correct Jacobian on the backward pass. And then if it is as refined as this, it would mean that okay, so every of these single steps we will need to save the current point, and that takes memory. So if you have a long network and training in parallel for a batch of data, you will need to remember these current points for all of that data and for all of the steps of the neural network. Then okay, then there are two solutions to that. One is that you use like more aggregate functions, which are available in the library already. So instead of maybe this explicit expression logarithm of the sum, there would be, I don't know, maybe there will be such operation, maybe not. But for sure there is a so this whole thing, so kind of cross entropy with the log softmax of the scores is available as a single operation, and then it so sort of the forward pass is faster, and the backward pass computes all these operations without using the memory, and likely also all of them are executed as a fused operation on the GPU, so it does not need the read-write of the intermediate results for each of the sub-steps here, also for the backward. Yeah, I don't remember exactly what is the cross entropy. Is it assuming the probabilities on the input or the logarithms of the probabilities? Logits, yeah. Yeah, then it would be if it's the logits, so the logits are here, the A. So then it's this last two things would be a single log. Yeah, okay, so that's one thing, that there are these composite operations, but the other thing is that so this what we discussed is called the dynamic graph. The um, code is executing, right, in the Python. Python is interpreting the code, and by the way of the execution, it's constructing this graph dynamically, and then you can backpropagate it. So this is very convenient for debugging also, that at some point of computation you could put a breakpoint and see, okay, what is my current state of the outputs, what are the inputs, so you could check this. But maybe it's not the most efficient way for running this in the training loop, because in the training loop you're gonna repeat this again and again, this forward execution and the backward propagation. So what PyTorch can do these days, it can compile this graph. What it would do, it would parse the code. So if you have this wrapped in some function, it would trace this function, sort of like executing this function maybe with dummy tensors and tracing what were the inputs to the functions, what are the dependencies. So it could do that. It kind of simulate the execution. It could then, from that, it could construct the graph, which is composed of the tensor operations. So there is a finitely many operations on tensors that you could do. So it could create such a graph, and then it could identify these little operations that can be fused together. It could decide what to say for the backward propagation, and which of this can be combined together on the forward, and which of that can be combined on the backward. So it's called torch dynamo or torch compile mechanism. It can do that. And then once you have this compiled model, you could then to apply it again and again to the same inputs. And yeah, you could even like optimize it to remove all the Python overhead, so it would just remember this sequence of the like low-level operations on the GPU that needs to be computed for the forward and the backward. So this can be optimized, right? But for our example, let's assume these are the blocks that we are backpropagating. And I'll go quickly through this. So then how it works. So this is our loss function, right? So this is the cross entropy, but with probabilities. And these are target labels. We don't need gradients with respect to target labels. The only derivative that we compute is this derivative of the loss with respect to this probabilities. And that's what it is in coordinates. Then, yeah, we are modular, right? So we go to the next block. So then what we have computed this far was the gradient of the loss with respect to the probabilities, and we need to compute the gradient of the loss with respect to the logits. So to kind of backpropagate this softmax function. Softmax function is this. So if you start expanding this product of the Jacobian, this row vector of the derivative is this Jacobian. So we start expanding this in coordinates. We see that it simplifies and expresses as something which can be written in the matrix form as this. Maybe two quick comments about this. So one comment is that so here we clearly see that to compute this formula for this backward, the input to this formula is this j sub y, but the result of this formula depends on the vector of probabilities. So we gotta remember the point at which we are differentiating this softmax. So we need to, when we were computing backward, we have to save the vector of probabilities. We could have saved also the vector of the input logits, but then we would need to kind of again recompute these probabilities. That would be redundant, so it's better to save the vector of output probabilities for like quick computation of this. Yeah, this is one node, and the other node is that so this is like n-dimensional input, n-dimensional output, but both forward and backward are linear time because, okay, we compute this summation once and then scale down each exponentiated coordinate on the forward, and on the backward, this is like, okay, so this is diagonal matrix and this is rank 1 matrix, so the things expand like this, so that you just calculate pointwise product here and a scalar product here, right? And then that's some vector. So again, it's linear time efficient, right? Now for this linear layer, yeah, we need gradients with respect to this biases, with respect to the weights, and possibly gradients with respect to the input if that was that was dependent on some parameters. Okay, maybe let me skip this, so we can kind of expand what we are computing in coordinates, and then according to the chain rule, compute all the parts. Again, so if we want the derivative with respect to this tensor of weights, we are out of that Jacobian vector formalism. So the derivative with respect to this weights still can be written as a matrix, but we would rather write it as a matrix of the same shape as the vector of W itself, because then we could treat it as a gradient. So that means like we can make a step on this parameter on this, okay, matrix of parameters, which is proportional to the gradient with respect to these parameters, and for that reason we would compute the so we could express the derivative with respect to all coordinates of this matrix again as a tensor of the same size as that matrix. Yeah, hopefully that makes sense. Okay, let me skip this. So this is some summary what we've discussed so far. Also, like to discuss on the practical side. Yes, of course, in PyTorch there is already such function softmax, but suppose it was not there, then what we can do? We could do this on the several again levels of detail. We could compose such a function out of existing operations, just exponentiation and normalization. And then that would do, because each of these operations already has a backward, that it would work. But maybe in this case, each of these operations will be saving something for the backward. That means taking more memory. Then you could do one level below. You could define a model which has this forward and the backward functionality. And so the forward functionality needs to take the input and compute the result, but it also has to save something to know how to compute the backward. And in this case, we are saving this vector of the output probabilities, as we discussed. and the backward pass kind of receives the incoming derivative of gradient, pulls this vector of saved probabilities from this contact scene, and then implements this equation with that, right? And this is more or less how it would be implemented in the library, but of course maybe as a single operation compiled on GPU, and not as this composite function. But yeah, with this semantics. If you have something custom and you want to tweak the backpropagation, you can do that in that way. Or you want to create some layer for which is composed not of the standard operations which cannot be backpropagated exactly. So like if you say if you want to implement the implicit differentiation rules, then you would need that. All right. Now going a bit more general. So what happens if some input is used more than once in this computational graph? Then what happens then with our chain rule? It then works according to the rule of total derivative. So the function now is depending on on this input twice. Once through this function y and once directly. And therefore the total derivative is the sum of this. Okay, this dependence through the direct dependence and the dependence through the y. You could also like view it as, okay, we take this b, we copy it, and then one copy goes here and the other copy goes there. And then what we need to show or to see is that if we copy the input, then the backpropagation for the copy sums the gradients. So this we can formally also verify that, okay, so copying the input in this two parts is multiplying with such a matrix with once on these two diagonals, right? So that's a linear operation which creates two copies stacked. And then the backward pass, it would multiply the gradient with this matrix transposed, and this results in the sum of these derivatives. So in fact, we could like from writing the derivative of the composition as a product of this linear operators, a product of these matrices, we could derive all the chain rules and all these total derivative rules if we like. So it is kind of similar. Okay, and then what can we do with such a generic computational graph? So if you have some more complex dependencies, but it's still feed forward, right? It's not just like organized by stages of computation, but you say, okay, this I compute from this, that I compute from this something else I can compute from that. Then it is not automated, as far as I know currently, but what you can do, you could kind of sequence this graph. So you could organize this graph by layers such that in each layer, all the inputs to all of the computation nodes are already known, right? And then all the nodes in a single layer, then they can be computed in parallel. So that would be in principle possible, but I think currently to do that you need to manually create some computational streams that are working independently. Yeah, but I think that's true. Okay, that's true. Yeah, that works as well. And maybe usually there is no big advantage in parallelizing these different computational nodes, even if you have them, because there is already a lot of stuff to parallelize, like over the neurons, over the data. But in principle, it would be possible also like to really execute this in parallel. Okay, maybe this is like a not real practical matter these days, but for completeness, assume you have such a complex feed-forward graph, right? What then the backpropagation should do? Then it should do exactly in the reverse order of this sequenced graphs, and it can in parallel do this corresponding backward functions.
So sometimes happens that some of those computations are computed on different machines even, and then you have to somehow wait for each other, and then this is what is more like explicitly formulating this. Yeah. So you said with the layers, you can do it like also with formatting layer.
Yeah, maybe I should have not touched this at all. For that we go like distributed model parallel. You don't want to discuss that. And we are running out of time. Okay, few minutes to discuss about implicit layers. So what is implicit layers? We discussed a lot about explicit, that we say, okay, you have some function of the input, and this is going to be our output, and then we want to compose such functions and differentiate that with respect to all the weights and all the inputs. The implicit layer, it says, okay, instead of this, instead of the functional dependence, you have some equation on x and z, and you want that this equation holds. So what it means, so okay, so if you give an input x, then to find that, you need to solve for the root of this equation. So you need to find z which satisfies that equation, and this is going to be our result, and then we compute something with that. So example is, for example, okay, so the few examples. Let's say you have input is your matrix, and the output, as output you want to have its eigenvalue decomposition. You know what is eigenvalue decomposition. It is these matrices U and S that satisfy this equation. But how to find them? So to find them, it is not a feed-forward computation. It is some algorithm that iteratively doing some steps in order to, so it is some numerical procedure that has many iterations to find eigenvalues and the eigenvectors, right? So it is represented by an algorithm. Maybe if each step of this algorithm is differentiable, you can backpropagate through the algorithm. But this is what we will discuss, that it's not going to be necessary. That so you see that it is in this form, that it is some equation on the inputs and on the outputs. And as long as you have the procedure for solving this equation, this is more or less everything that we need to be able also to find the derivatives. Okay, so some other example, if it is the optimization problem, right? So for the optimization problem, you could write its stationary point conditions for the local minimum. It's going to be some equation. If it could be some differentiable equations, or it could be also like a fixed point equation that says, okay, I want, so the fixed point equations, they arise quite a lot in neural networks, in recurrent models. So if you have some time iteration like this, x k plus 1 is maybe some sigmoid function w x k plus x0 maybe, right? And you kind of, k is the time, so you iterate this again and again, and then it does something. So this is like recurrent neural network weights W. Or it could also, like this fixed point equation, it could also represent deep equilibrium model. So, okay, 5 minutes. Okay, I skip the deep equilibrium model. You know, so on our lecture page, I put here a link to a very nice tutorial about this implicit differentiation. And you could look at the first lecture from that. There is a nice introduction, like what it could be useful for in today's context. What are the interesting, useful case of these implicit layers, and it explains. Okay, it explains all the details, and there are even notebooks with the examples. But maybe what we can do with you is to see how it works, why and how it works, right? So this we can do in 5 minutes, really. So we said we have this function g, and now the constraint is that the function must have as many dimensions on the output as this z variable we are solving for. Otherwise, this is not going to work. So this is maybe the main constraint. So we have some vector valued equation, g of x and z equals 0. Yeah, I guess if it's not that, then we cannot solve even this equation for that. So this is like a prerequisite for this to define more or less to define that uniquely in the first place. Maybe it's not necessarily to define it uniquely, but it's a prerequisite for that. All right, and then under some more conditions on this g function, which are maybe not that essential, this function is locally, so then the solution, the z solution is locally really a function of x. So what it means, so this is an example for this equation, x squared plus z squared equals 1. So this is an implicit definition of what z is. And we can solve it for z if you like. In this case, even we have analytic solution with the two roots. But maybe if it is a more complex equation, like a higher order polynomial or system of polynomials, you might have an algorithm, but you will not have like an analytic formula for the solution. Okay. And this algorithm is able to find some solution. Let's say this is a point satisfying this equation. So this defines z. And then what it means that locally it is a function. So if you change the x a little bit, then z in the vicinity of this point is really a function of x. So it's even if this equation has two roots for z, this one and that one, then locally around this point it's only one root, and so it's only a function. And then the trick, what we do with this, is we take this equation, the defining equation, and we take its total derivative with respect to the x, with respect to the input. If we expand this total derivative, it turns out that we have this partial derivative of the constraint with respect to the x, the partial derivative of the constraint with respect to z, evaluated at the current solution that we have, and the derivative, the derivative of this z, which is this implicit function, with respect to the x. And then from this identity, I actually can express out this derivative of the implicit function z with respect to x. So then we need just to invert this part, and we got this. And here the minus is missing. And so what it like, okay, in this example, we could do this simply, right? Let me do this in this example. So we have then dz dx will be what? So derivative of the constraint with respect to z. That's 2z minus 1, right? And then derivative of the constraint with respect to x. That's 2x, right? So just this. And then our chain rule is, okay, we take Jacobian of the loss. So suppose we have some loss function of, right? So suppose we have some loss function as a function of z, then it's Jacobian is, okay, derivative at z, and then we need to multiply with this. So this is going to give us x over z, right? So this is going to be our chain rule. And the point is that to compute this, we only needed to differentiate these constraints in x and z, which is simple. And this, so here we need to solve some linear system maybe with this incoming gradient, which could be a bit more complex. But otherwise, what we have avoided is that if this solution was given by some complex algorithm, we don't need to backpropagate this algorithm, but instead, knowing the solution we know and the derivatives of these constraints, we could compute the derivative of the loss with respect to the input x, and then this works for this I don't know, differential equations for optimization problems for these systems of things that we are solving, and this could be a part of your trainable differentiable network. I am over time. Thank you.